All right, hey y'all. So what I'm going to do with the rest of section 7.5 that I'm going through now is it has three more examples, and I don't want to do them all at once, and I don't think you want to listen to them all at once. So they're going to be different videos. That way we get shorter lengths of time where me and you have to pay attention. Um, yeah, I don't want to do it. So I'm going to share this next example with you. So this next example is a block sliding down a wedge, and we're going to allow the wedge to slide across a plane, the floor, however you would prefer to think about it. And we're just going to sort of analyze what would happen with Lagrange's. We're not going to make it do anything. We're just going to, how would that work? So it's relatively simple, just because you just kind of just do. So one thing to start off with is I defined Q1 and Q2, which if you look, we're going to pretend this is a very well very well representation of what a Q sub 2 would look like. But basically Q1 is that block sliding down, and Q2 is just your normal old x-axis based on what I drew down here. So what we're gonna do first is we're gonna look at the Lagrange. I feel like at least once per day. I don't know how to pronounce it. Anyway, we're just gonna look at that basic boy. So what we want to do is we want to analyze both of the kinetic energies that could happen. So since our wedge is moving right here, it's got a kinetic energy of 1/2 that big M times the changing Q2. That one's pretty simple. And then our little black, it's gonna be harder. I'm gonna tell you right now. It's gonna be different. So basically what's gonna happen there is we're still gonna have 1/2 mass of the block is this little m. Here's where it's about to get really gross. It's gonna both move in Q1, which we're gonna break apart into kind of like their x and y components, because we know x and y a lot more than we know the arbitrary value of Q1. And then it's also that Q2 is also gonna affect it. So we're gonna start with the x part. And then I'm gonna break it up into what it would look like as a velocity, and then I'm gonna write squared over each one of them, because that's what happens to the velocity. So the first part, we move in an x direction, which is going to be starting off with that Q2 dot, because we know for sure it's at least moving with the wedge. Then what it's going to do from there is we're going to use trig functions to sort of simplify Q1 with Q dot 1, which I'll write right there, into x and y coordinates. So basically, it's just going to be Q dot 1, Q1 dot times cosine of alpha. And alpha, this angle up here. So you can see how that would work. Its cosine would be this. However it moves with respect to that is going to be on the same plane as Q2. Well, that's going to get squared. And then the next deal here is that in the y direction, it's going to look a lot like that second point in the x, which is going to be Q2 dot, and this time sine alpha, and all of that is going to be squared. So I'm going to pull it down so we don't have to, so we can follow what I'm doing. I'm going to write that out nicer now because it's gross. So what that ends up doing is we're going to get 1/2 mass, that little m, times, so what I'm going to do is I'm going to factor it out, and when you do this, I'm going to write the last version, but basically you're just where everything, you're going to realize that cosine squared, sine squared are going to have some of the same coefficients, and this was supposed to be a Q1, is what I'm realizing. Okay. I think I said Q1 and I just didn't oblige. Either way, they're going to end up factoring out to be 1. So you're going to drop a lot of stuff, and it's going to look like so. Q1 plus Q1 squared plus Q2 squared, Q dot 2 squared, plus 2 Q1, Q2 dots over both of those, and you're going to be left with that cosine alpha, because you're going to have one of those that does not cancel. Great. So that's what part of it looks like. I'm not going to lie to you. It's really ugly. So now we're going to combine them, and when we combine them, what I would like to point out is that this and this, I'm going to combine into one term. That way I don't have to write it twice. So we end up getting that our total kinetic energy is going to be equal to 1/2 that big M plus little m. And this is where that Q dot 2, just realizing I left that out, Q dot 2 squared is going to come in handy. It's just going to be that times Q 2 dot squared. Yeah, all that. And then we're going to have the rest of everything else just lumped together in this ugly heap right here. Cosine alpha. Great. Now I'm gonna pull you all back up to the image. What we're gonna do with the image is basically we're gonna try to find the potential energy from it, and potential energy of wedge. Easy, it's on the floor. It has no potential. Potential energy of the block. That wedge thing. However high up on the wedge it is. So what we're going to do is we're going to bring it back down here to where we were working. We're going to know that our potential energy is going to be equal. I'm going to make it negative. That way I get a positive. I can choose Q, or that the mass of the wedge, which is M, times G, times Q1, so wherever its position is in Q1 space, times sine theta, because we only care about the up and down position of it. That's it. So now, here's the really gross part, is I'm going to write that all into the Lagrange. I'm just going to write it. Okay. All right, so that's what we end up with. It's long, it's gross, but it's the truth. So the next thing we're going to do is we're going to take the Euler-Lagrange equation. So that's this bad boy. You should definitely have memorized. It's useful. You should have this useful information memorized because it's useful. Straight from the brain of Sierra. All right. So we're going to look at that one and then also its variation in Q1. Okay. So we're going to do Q2 first. First part's pretty easy. It's 0 because we don't have a Q2. So the Lagrange and the derivative of the Lagrange with respect to something that's not there is 0. It's all a constant. All right. And then we'll end up time derivative of the derivative of the Lagrange with respect to Q2 dot, which is going to be M, big M, Q dot 2 plus M Q plus Q1 cosine alpha. Nailed it. Okay. So that's what we get left with. And what the textbook then does is, instead of taking the time derivative, it sort of shows you a different way of thinking about it, which is basically, since the time derivative of that function is 0, this function equals a constant. So what we're gonna do is we're gonna set that function equal to a constant. Yeah, that's really what it does. It's literally doing the exact same thing. It just wants you to be like, since we're doing the wedge, we're gonna think outside of the box. And you're like, great, textbook, you're so funny. Anyway, that's what it ends up giving you. That's equal to a constant, and then it's like, now take the time derivative. And you're like, thanks. It was really weird when I read it, and then I realized it just wanted us to like think about it in a different way. So we end up getting M over M plus M Q1 cosine alpha. Yeah, so that's what we get. So not only did I take the time derivative, I also solved for Q2 dot dot. Trust my math. If you don't, you can check, but I definitely copied out of the textbook, so I know my math's correct. All right. So anyway, on the second equation, so this time with respect to Q1, I'm gonna post the notes, that way you can like see them all at once. But we can take this with derivative with respect to Q1, which leaves us with just this last term right here. All right, so we're gonna write that out. Mg, we drop Q1 because it goes away because of the derivatives. And then we're going to be left with the time derivative of something that looks very similar to the second part of, to this part right here. I don't want to say it out loud. It's going to be confusing. Ah, great. Whoa, not great. I have no idea where it just took us. I think wow. Wasn't that beautiful, everybody? Okay. We love OneNote. So what we're gonna do with there is, this time it's like, yeah, just take the time derivative. I'm like, could have done that on the first one too, but you know, you just want it to be spectacular. Right, that's what we get for the time derivative of it. And now what we're gonna do is we're gonna solve for Q1. But before we do that, I would like to point something out. Because we have two unknowns, so we need two equations. So Q dot dot 2 that you see right there, I'm gonna plug in this. Okay? So I'll kind of do one of these numbers where I don't have it fully memorized, so I'm gonna look at it. Q1 dot dot plus M over M plus M Q. Actually, you know what? No, we're not doing that mess. I'm gonna use an eraser like a smart person. Okay. I'm gonna solve for Q dot dot 1 before I even touch that, because right now these cancel. And that's nice for me. Q dot dot 1 will be equal to Q2 dot dot cosine alpha. Yes, cosine alpha. All over M. I don't know why I wrote it like this. Okay. That most certainly was not the most correct answer I could give. Because it's just G sine alpha minus Q2 dot dot cosine alpha. Right, here's where it gets messy. That's where I'm going to plug all this in. Q2. Yeah, it's going to look really freaking gross. Okay, let's go. G sine alpha minus, it's going to be plus this time. That other equation's a negative. M over M plus M Q dot dot 1. And it's going to be cosine squared because it's going to be cosine alpha times cosine alpha. Great. And bring down Q1 because now we have to separate our Q1s. Isn't this fun? So what we're going to do is I'm going to kind of like move it and separate it all in one. M over that big M plus M Q. I forgot my cosine. My cosine squared. There we go. Okay, so that's going to be my separation and my bringing it all to one side, wrapped up in a pretty little bow. Then I'm going to divide all that to get Q1s. Q1 is going to be equal to this super gross fraction. There we go. Now, if you have Q dot dot 1. Now, if you have the strongest desire, you can plug this bad boy back into this guy, this blue guy up here. I don't have the strongest desire, so I'm gonna leave it there. But that's all that this example really goes over. So I'll do the rest of the examples in a different video. I'm starting to go back through the videos and add the notes that I have written down on a piece of paper to each one in the description section below. So you can access this. I am aware that I chose a poor method of sharing them, but it's the method I've gone with. So that's what it is. All right, enjoy.